Hi. So in this talk, I'd like to discuss the connection between mergers and bulges using observations from this galaxy NGC 5746. One of the motivations from the study comes from the observations that the frequency of classical bulges increases with stellar mass. I'm showing here a plot from Gadotti 2009, where you see on the y-axis an indicator of star formation versus stellar mass on the x-axis, with a red sequence in the top and the blue cloud in the bottom. And the points represent different types of bulges. And as you can see, when you go above 10 to the 10.5 solar masses in stellar mass, most galaxies have classical bulges or are ellipticals, but there are fewer and fewer pseudo-bulges or bulgeless galaxies. And this idea is consistent with the fact that classical bulges could be built by mergers and that the frequency of mergers increases with stellar mass. However, there is one slight complication, is that there are some massive galaxies that don't have a classical bulge. And because of this correlation between mergers and classical bulges, this has often been described as a challenge to lambda CDM and to the idea of a hierarchical buildup of galaxies. However, before we can start really thinking about the challenge to lambda CDM, we have to understand if these massive galaxies with no classical bulge might have had very quiescent merger histories, or maybe also the link between mergers and classical bulge is not direct, and there are mergers that do not create classical bulges. Simulations could potentially help, but simulations are they're improving, but they're still struggling to produce the realistic populations of bulges. Here is an example looking at the TNG50 simulations by Gargiulo, showing on the y-axis the Circic index of galaxies as a function of their stellar mass, with the classical bulges here in red. And you can see that there's no trend with stellar mass at all. And even at high mass, most of the bulges in that simulation are not classical bulges. This means the simulations do not yet have a predictive power to look at the correlations between bulges and mergers. However, there's still interesting results in the simulations. So for instance, here this plot is showing the Circic index of bulges as a function of a mass that is accreted. And there are two important conclusions to see from this plot. The first one is that there are galaxies with really quiescent merger histories. Even in that high mass range, there are galaxies that have very few accreted stars. And the other aspect is that while in general, the Circic index of galaxies tend to increase with the fraction of accreted stars, it's a lot more complex than this, and mergers do not always affect the central regions of galaxies and do not always create classical bulges. But because the simulations are not perfect yet, then it is a good time to think about how to test this with observations. And one galaxy that is particularly interesting for this is NGC 5746. It's a very massive disk galaxy with a mass of 10 to the 11 solar masses. And you can see on the picture, it has a very large extended disk. In the center, you see an X, and that's a pseudo-bulge, a bar, actually, seen on its side. It has a nuclear disk also in the center. But what Barenthal and Cormendy showed in 2012 with deep HST images is that there's no classical bulge in the galaxy. So when they did decompositions of the light profile of the galaxy, they did not find any central component with a high Circic index. And so they concluded that the galaxy is a giant pure disk galaxy with no sign of a merger-built bulge. And then they described how this could be a challenge to lambda CDM. So what we wanted to do in our study is to get some Muse data for this galaxy to look in more detail at its formation history. So we got data along these two pointings in NGC 5746, one central pointing and one on the disk, for 6 hours of observation time in total. So we got really deep data that we could bin to a signal to noise of 100 so that we could look at stellar populations with good confidence. And we fitted all the spectra with PPXF to decompose the spectra into different stellar populations. I'm here showing also the velocity and dispersion maps, and in the paper we discuss the kinematics, but here I am going to just focus on the stellar populations. So these are the mean mass weighted maps we get from the PPXF analysis, so the age, metallicity, and magnesium over iron maps for the galaxy. What you can see is we have a thin disk here, right, which is a little bit younger, a bit metal rich and alpha poor. So this is the thin disk. On top of that, we've got a layer of a thick disk, which is older, more metal poor and more alpha rich. So this is the disk. In the center is your bar and peanut structure. And you can see already that the bar is old. Here, all the central regions are very old. You can also see here the nuclear disk, which appears really quite distinct from the rest of the galaxy in terms of chemistry. So it's very metal rich and alpha poor. And it also here is very old. So the nuclear disk is quite easily seen in the stellar population maps. Now we can look at this in more detail because we don't just have the mean mass weighted maps, but for each spaxel, we can get the star formation history. And so we can build the star formation histories for the different galactic components. What we find is that the star formation in the galaxy peaks at very early times. So the galaxy formed very early, but then star formation continues at a low level in the thin disk of the galaxy. And so that's what I show here on this plot, the star formation history for the thin disk with two different regularizations in PPXF. You still see star formation here at late times. However, if we look at the star formation histories for the bar and the peanut, we see a very different picture. We see that in the bar and the peanut, there are no young stars at all. And what this is telling us is that the bar did not form at late times, because if a bar had formed, say, 2 gigayears ago from the thin disk, then all the young stars in the thin disk would have been collected into the bar, and we would see those young stars into the bar, but we don't. So this is telling us already that the bar did not form too recently. But we can also go one step further by looking at the nuclear disk, because we also find that the nuclear disk is very old. And if we believe that the nuclear disk formed from gas inflows along the bar, then the nuclear disk must have formed after the formation of the bar. And so the oldest ages in the nuclear disk are telling us about the time of bar formation. This is an idea that's been used by several papers, including Gadotti et al. In 2015, and more work also is being done in the Timer survey on that topic. And you'll see talks this week from Dimitri about this. So from the age of a nuclear disk, right, and the fact that it's very old, we know that the bar must have been in place for at least 10 gigayears, maybe even 12. We don't know for sure because we don't really have a good age resolution at that level. So a bar that would be 10 or 12 gigayears old seems very extreme, because that's very, very early for a galaxy to have a massive disk in place, but it's not unique. And we have examples of other galaxies with bars that are around 10 gigayears old. And this is also consistent with the general idea that massive galaxies mature faster and they form their bars earlier. So NGC 5746 is probably a bit extreme, but definitely not unique and not weird in that respect. But for sure, this is a case of a very long-lived bar. Another thing that's interesting in this galaxy is that we can also decompose each spectrum, not just into star formation histories, but look at the full distribution of metallicities and ages for each spaxel. So what I'm showing here is for one spectrum in this spaxel here, the distribution of the weights from PPXF in this metallicity versus age plane. So this is telling us the distribution of populations we need in that place in the galaxy to reproduce the observed spectrum. And what we see is, as expected, we have an old metal-rich component, which is consistent with the galaxy forming very fast. But what is more surprising is this younger, more metal-poor component, because this is not how chemical evolution works in a galaxy. You don't go from metal-rich to metal-poor if nothing weird happens to your galaxy. So this is a bit surprising. But our best interpretation for this component is that these are accreted stars. So that if you look in this plane, on the top here, the metal-rich stars are the ones that formed in situ within the main galaxy. And these ones here are accreted. We think they're accreted because they're more metal-poor. And this is because of the mass-metallicity relation in galaxies. So that lower metallicity galaxies are actually, so that lower mass galaxies are more metal-poor. Right? So if you see metal-poor stars, they must come from a low mass galaxy. And if we sum the mass of this component throughout the galaxy, we find that this should correspond to a merger with about a 1 to 10 ratio. And possibly if we believe that the stars here are coming from the merger and that the age distribution stops around 8 gigayears, possibly the merger happened around this time from, say, 6 to 8 gigayears ago. Now you could also argue that these metal-poor stars could be formed from metal-poor gas accreted by the galaxy, and that could be a possibility. However, what we believe is that if some metal-poor gas had been accreted in large quantities, it would have mixed with the gas in the main galaxy and would have diluted the overall abundance of gas in the galaxy, so that you would just see a drop in metallicity and you would not see these two separate populations here. So we think that this bimodality in metallicity is telling us really that this was the accretion of a satellite galaxy and not just diffuse metal-poor gas. We can map those metal-poor stars and we see that they are distributed throughout the galaxy, which we can compare to the distribution of the in-situ stars. Here we see the old in-situ stars that are more centrally concentrated, and we find them mostly in this central bar region and a little bit throughout the thin and the thick disk. And here you see the slightly younger in-situ stars. And what's interesting is that they don't populate the thick disk too much. So we think that actually the merger that happened around 8 gigayears ago probably did not cause too much vertical heating, because these stars here do not populate the thick disk too much. So the merger is not responsible for the creation of most of the thick disk, right? Because most of the thick disk is actually older than the merger, and the merger did not thicken anything in the galaxy. However, this satellite is still important in terms of galaxy structure because it contributes about 30% of stars in the thick disk region. So in terms of properties of a thick disk, there's still a decent fraction that's accreted. So that's still important for the galaxy morphology. However, the merger did not really alter the morphology of the galaxy because it did not destroy the bar and the nuclear disk that formed much earlier. And also the merger did not create a classical bulge in the galaxy. So even though the merger did bring a good number of stars into the thick disk, apart from that, it did not dramatically alter the morphology of NGC 5746. So to conclude, as the organizers asked us on what does this tell us about the formation and evolution of bulges, well, we have here a case of a massive galaxy with no classical bulge, and we've been able to track its formation history. And what we found is that it mostly had a recent, relatively quiescent merger history. There's no sign of massive mergers recently. There is possibly a 1 to 10 merger about 8 gigayears ago, but this merger had very little impact on galaxy morphology. It did not create much disk thickening, and it had no impact on the central regions. So it did not destroy the bar and the nuclear disk. So this is another case of a galaxy also that had a very long-lived bar and nuclear disk in spite of the 1 to 10 merger. So another final message that I want to leave you with is that With MUSE, we're now in this great position where we can probe at the same time the detailed structure of galaxies, so the star formation histories and the kinematics and the metallicity distributions, and the merger histories. And so at the same time as simulations are improving and I'm making better and better predictions, we can start probing those predictions with observations and look at the effect of mergers on disks. And my final message is that this is best done with surveys of edge on galaxies, because accreted stars are best seen in the thick disk region. This is where the fraction of accreted stars is highest. And this is where they're easiest also to see because you're not contaminated by the light from the thin disk. So with surveys of edge on galaxies, we are going to be able to see both the merger histories of galaxies and the bulges and the thick disk, and try and connect all of those directly from the observational point of view. Thank you for listening, and I look forward to discussing this with you during the week. Thank you.